All right, halfway switch your computer. We're going to be back in about 10 minutes, okay? If you have your computer still kind of up and running there, can you put the battery on balanced or low or whatever, just so they don't die on us? Because I was going to postpone this for a minute, but I've already done what I've done, so here we go. Check it 1 through 4. Here we go. Ready? So I'm going to come back to these notes. I want you guys to write down in just a minute, but we're going to check our homework first. So I'm going to ask for, you guys have already kind of discussed as a team what you're looking at. We checked this one? Yes? Yeah. We did check this one. All right, if you did not check it with me, then here we go. I think we only got partway through. So what we have is this weird COCl2 gas plus energy and carbon monoxide yields carbon monoxide and chlorine gas. If I increase the temperature, to you, does temperature look like it's a reactant or a product? It's a reactant, because we can see it as a reactant right here. So if I increase reactants, which way do I need to shift? Everybody. Shift left or right? Right, because that's going to achieve decreasing the energy again and allows us to even out back to equilibrium. Okay, so increasing the volume does what to pressure? So use your box of air, everybody box of air. Take your volume and increase it. What does that do to pressure? Decrease. Okay, so, problem is, and I'm going to modify how I explain this a little bit. I'm going to take it 2 different directions. If the stress is I now have a big volume, you still have to count moles of gas. So, Will, how many moles of gas are on the reactant side, Will Evans?
Teachers with 4th period planning who want to participate in the EVOS training should report to mobile units 3 and 4 at this time.
This is number 2. This is number 2. How many moles of gas are over here?
4.
Mm-hmm. There's a... Are you tripping? What are you talking about? Look at this. There's a... What coefficient is in front of CaCl2?
Oh, yeah, 1.
A 1. Sorry, it's kind of hard to see right there. But yeah, there's a 1 there. So there's only 1 mole of gas because you're counting coefficients. Olivia, how many moles of gas are over here? 2 moles of gas. Okay, so everybody, you have a large box of air. What fits better, 1 mole of gas or 2 moles of gas? 1. Okay, what's going to fill the box of air? 2 moles of gas. So automatically I'm thinking shift right because that's where the 2 moles of gas are. But that's just the volume debate. That's just the volume. So we're looking at how pressure is also involved. Here's what you're thinking. Increased volume does what to pressure? Decreases. Okay, so now you have too few collisions with the container wall, because that's what pressure is, right? Colliding with the container wall. So, I've got too few collisions. I got to fix that. So, will 1 mole of gas or 2 moles of gas fix the low number of collisions I've got going on? 2 moles. So, I'm shifting to the right to create double moles, which would then help with the collision problem, which would increase my pressure once again, and I'll be back at equilibrium. So, you can think of it strictly in volume, or you can think about how volume and pressure are related. But this is definitely the most convoluted thought process. Are we okay? That's not the easiest one. Well, yeah. You good? No, I think it's sometimes. All right. I want you to re-explain this to your peers at your table. Turn and talk. Re-explain.
So depending on how I was thinking probably in the middle, so like based on increased
Okay, come back to me. 3, 2, 1. Harshita's table. C. No shift. For Garrett's table next. D. Why shift left? You're correct.
to balance.
Okay, so we've added a product. So if we add a product, we shift the opposite direction, which would be a shift left. Heating the reaction vessel. Remember, the reaction vessel is just the big container that the reaction's taking place in. Doesn't really mean anything special. Josh's table, heat the reaction.
We said shift right without increase the heat energy.
Increasing heat, which increases energy, would increase the reactants, therefore it needs to shift the opposite direction. Anytime you increase something, don't go towards it, go the opposite direction. Anytime you decrease something, what do? Go towards it. Right, that's going to make more of it. All right, so let's keep rolling. 3, Gwen's area. Give me A. Are you questioning yourself, or is this a common answer? Okay, so decreasing the temperature, which is a form of energy, will cause a shift right, because energy is a product, so I'm shifting towards it because I've decreased it. Emily's table, increasing the volume.
Shift left.
Okay, so tell me your thought process here.
3 moles on the left side.
So 3 moles, and remember we have to talk about gases because those are the gases that take up the space. So 3 moles of gas versus 2 moles of gas. Okay, so why are we shifting left?
Because the collisions.
Huh? You're correct. Tell me why.
The amount of collisions more on the left.
Okay, so you're saying an increase in volume causes a decrease in pressure. So the problem is too few collisions. That's what your thought process is. So I want to fix the too few collisions. So fixing it will come from a shift left because there's 3 moles of gas. That was the entire thought process.
So if there's more moles of gas, more moles of gas, that's where it shifts to.
If the problem is too few collisions, yes. If the problem is too many collisions, oh no, I got to find a way to get less collisions, so we go to the fewer moles of gas. Okay, very good. Good thought process here, guys. Will, next. Heat the add O2.
Oh, add O2. Shift right.
Good. Olivia's table, D. Heat the reaction. Good. So this is a heat energy. We increase the products. We go the opposite direction. Max area. Last, increase pressure.
Shift right.
Good. So here's that question you guys just asked. Increasing pressure causes too many collisions. Too many collisions is the problem. So to get away from too many collisions, you're going to shift right because there's only 2 moles of gas there versus 3 moles of gas. Okay. Next, I want you to hold up your left or right hand for A. Hold up your left or right hand for A. One or the other on this one. That means like you shift left or you shift right. This is right. This is left. L, left. Okay. All right. So I see a lot of us doing okay. So pulling the reaction vessel means I've done what? Decreased energy. Decreasing energy. I want to go that way. So we're going to shift right. Good. Increasing the volume. It's because I want to make more. If I take it away, I decrease it. Left or right? Come on. Let's go, folks. A lot of you guys are saying left. So how many moles of gas are here? 5 moles of gas. How many moles of gas are here? Nope.
3, 4.
That's a liquid. 2 moles of gas. So we're still in good place. Like we're still in a good place because it is less. But regardless, it is only 2. So increased volume does what to pressure? Does what to pressure? Decreases pressure. So now there's too few collisions. Too few collisions. That's the problem. I want to increase collisions. Which way do I go?
More moles.
More moles. That would be a shift left. Good. Adding sodium chloride. Everybody. I like Hunter's response. Okay, so no shift. Good. Everybody for the next one, D? I like this one. Nobody else is doing it? Or just okay, no shift. Okay. And then increase the pressure. I need to see your hums.
Increase pressure.
Increase pressure. Oh, too many collisions. If I have too many already, I need to go to lesser, which would be a shift right. Okay, so give me how you feel in the shots out of 10. Like 10, I am the master. one, like, what? One and 10. 1 between 1 and 10. Okay. Alright, come back to me. Here's the last bit I need to explain.
You want to stretch it out?
Yes, this is the last, these are the notes I didn't get to give you on Friday. Okay? So, while we're finishing this up, we'll be good to go after this to work on our next activity. Nathan, if you could start writing this down, that'd be great.
Is it still what we call it leave?
Please write down on the board.
I've gone through 2 of those in here. Just an FYI. I appreciate that. I appreciate it. I'm sure it's organized though.
Mac, are you done with this? Will? I'm going to slow you down a little bit because I want to talk about these 2 things first. Alright, so when you get here, thumbs up for me. Okay. Because the common ion effect one will take me a minute to explain before you start writing down all that stuff. Alright, so we already know a lot of the ways that we can shift equilibrium, but we want to make sure that we can elaborate on some of those more intricate ones. Like, if I know something's endothermic, that's actually because I can see a delta H, or I can see where energy is placed in the reaction itself. So if it's endothermic, delta H is what? Positive or negative? Positive. That means energy is being absorbed into the system. So if it's being absorbed, is it listed, energy listed as a reaction or a product? It's being absorbed into the reaction. It's got to be a reactant to be absorbed. If the product's being produced and it's kind of long gone at that point. So listed as a reactant. So that's for endothermic. So for exothermic, delta H is, so it is released. So kind of follow the same thing, released, and it's listed as a product. Good. So those are 2 things to look for the temperature and energy changes. Second, we already know that interchanging or modifying reactants and products are going to kind of disrupt equilibrium, and then it will cause a shift. So that's pretty easy to see for most of you guys. That's probably the easiest of them all. So the common ion effect is a weird thing. Okay, so what happens is, like, here, write this example down. Silver chloride solid equilibrates to silver ion aqueous and chloride ion aqueous. So we have this equilibrium. Silver chloride solid equilibrates to ion and ion. So let's say I add silver nitrate. Okay, well, do you guys see silver nitrate in this reaction? At all, yay or nay? No, there's no silver nitrate in there at all. So we're like, oh, no shift, right? It doesn't affect it. Well, actually it does, because inside of silver nitrate there are 2 ions, silver and nitrate. Now you start to see some similarities. What of silver nitrate is the same as what's in the reaction? Silver ion, aka it's a common ion. It's common in the equilibrium and in this new species that we're adding into it. So yeah, adding silver does cause a shift. So technically I'm adding, or I'm increasing the concentration of silver. So in this equilibrium, which way will that shift? Shift, probably, come on, loud and proud. Left, because I've increased the product, so it's going to shift the opposite direction. So though it's not exactly the same thing, it has a common ion. So do we understand that common ions can affect equilibrium? And you just have to look for the single ion. And this is usually only in solutions. It's got to be like in an aqueous kind of setting. So this is another form of the common ion effect, which is this definition right here. I'll leave that right there for you. Yes. It'd just be floating in solution. It doesn't do anything. Right. So that's the first example of a common ion effect. A second example, I'm going to write a different color here, is if I add lead to nitrate. Okay. So lead to nitrate. So what am I actually adding in that aqueous solution? What two things? Lead what? 2 plus and nitrate, right? All right, do you see lead 2 plus in my equilibrium? No. Do you see nitrate in my equilibrium? No. So at first we're like, no, shift, right? Doesn't have anything to do with equilibrium. There's no common ion. But so this one's kind of the weird one. It's the common ion effect. It's like, what can one of these ions do to equilibrium? It can actually do something, and it's a precipitate. It's going to form a precipitate. So what happens is lead. Everybody look at the solubility rules for me. Look at the halides. So to share the progress right now, we don't have them nearby. Share. Do you see the bromides, chlorides, and iodides? So they're normally soluble except with who? Silver, lead, and mercury, right? So here we've caused some sort of new lead ion to come into play. So the lead 2 plus will actually come in here. So look up here just so you're not messing up, because there's going to be a lot of drawings and stuff. Okay, so lead 2 ion comes in here and says, hey, chlorine, let's make a precipitate. Okay, so it's going to make lead 2 chloride solid as it precipitates out, right? All right, so it has taken hold of chlorine and it's made it drop into precipitate. So what has it done to one of these ions? So it's lowered, right, it's taken away the chlorine. So it's lowered the chlorine concentration by way of precipitate. So now we know that chlorine's decreased in concentration. Which way will this shift it?
Right.
It will shift right, because the problem is now you have too few chlorine ions, you need to make more. So the common ion effect is either one of two things. Simply an ion that is in common, or some other thing that's stealthy, and it comes in and attacks, and it precipitates something out, and that precipitate now decreases the concentration of something, and that something you just have to figure out what it is. In this case it was chlorine, and it causes a shift. So that's the weird one. We don't see it too often, but you'll see it in the simulation agent today. Yes, so so the first reaction here you have written down, right?
Yes.
Okay, so the common ion effect comes in two flavors. One, just adding an ion that is in common with what's in equilibrium. So that's just going to cause a shift left immediately because it's the same exact concentration, or the same ion. The second version is adding something that's not strictly in common, right? There's no lead 2 nitrate, but that's what we have. But instead, it's one ion kind of interacts with one of these ions, which lead's not going to interact with silver. It's positive and positive. Like, I know it's the 21st century, but it's just not how chemistry works, right? So it's going to interact with the negative, because opposites will attract, and that will cause this to precipitate out as lead 2 fluoride. And that precipitation makes a solid. No more free ions. So there's no free fluoride ions. That means that that has decreased in concentration, which now will cause a shift right. Yeah. So those are the two more difficult ones. All right, and the last two that you already know about are changes in pressure, which in volume and pressure have a common kind of relationship, which is Boyle's law, and adding an inert gas, which we've already seen that twice now. and it's group 8A gases, like helium, neon, krypton. Any of those are inert gases, which means that they don't react. So if they don't react, they don't cause heat shifting in equilibrium. When you get done what's on the board, you're going to do questions 8, 9, and 14. 8, 9, and 14.
Yeah, I know. Take a little bit. That's what you wake up. No, I
Guys, let's dumb this down for me. I know it says make more products. Dumb it down. What does it want you to tell? What does it want you to figure out? How to shift right, not left, because those are the reactors. So it wants to make products. It wants to know how can you shift right.
No, it does work. Why do they sound different when I say it on your side?
All right, let's do number 8 and 9. Back to me. 3, 2, 1. Okay, so for the first one, we're looking for shift right. Nathan, give me one example that would cause a shift right.
Increase pressure.
So if you increase pressure, that's going to cause too many collisions, right?
Yes.
All right, so Nathan, which way will we want to favor? If I already have too many collisions and I want less.
Decrease from increase.
Alright, so are you with me? Okay, so this is going to be our decreased pressure one, because there's how many moles of gas over here on the reactant side? 1 mole of gas. And how many moles over here on the products? Nathan, thank you, 2 moles of gas. So if I have too few collisions, because of this decreased pressure, I'm going to shift right to make 2 moles of gas, which will cause a lot more collisions. Another, Peyton?
We said add N2O4.
Okay, so adding a reactant, which would be N2O4, will cause a shift right. Good. Ethan? Say again? Increase the volume. Good. And that's going to cause the bigger spaces, 2 moles of gas would feel better. Good. Parker?
You could heat the reactor.
So if I heat it, how did you get to choose, like, heat it or cool it? What did you look at?
Well, heating the reactor will put energy in the left side.
No, heating, so it'll say heat the reaction vessel. You don't get to choose where the heat is applied, but this up here will tell you where the heat is being utilized. This is positive, right? So this means this is endo, so where is energy? On the left, right? So this is correct, but it's because the energy is already applied, because it's endo, it's already applied as a reactant. So if you increase this by heating it up, it's going to increase energy, which will cause a shift right, because it's acting like a reactant. One more, Mac. Remove what? NO2, nitrogen dioxide, right? So removing a product will cause the product to continue to get made, which will be shift right. I believe that's it. Okay, moving on. The second one, this was number 8. Number 9. Alexia, how would I cause a shift right? Because again, this one still said products. Yes, for this one, because this is XO, right? So where is energy listed here, guys? On the products, so I'm going to say plus energy. So if she decreases temperature or decreases energy, it's going to be a deficiency on the product side, so that will cause a shift right. Alex? Increased volume would cause, why do you say that?
Because when you increase the volume, it favors the side of foreign moles, gas.
Can you count the moles for me?
Oh, never mind. I looked up to
Good, so that's one thing we want to look for. There's 2 moles of gas here, and there's 2 moles of gas here, so the volume won't do anything great for us. It could just cause a no shift. Langston?
Did you add into the rules?
N2, okay, let me take somebody else for the next one. Amina?
Decrease.
So pressure and volume have a relationship, right? So Alex just mentioned the volume, so we counted the moles already, so there's 2 moles of gas on both sides. So that tells everybody volume's not going to cause any changes and pressure's not going to cause any changes. So we'll point that out too. So change volume or change pressure, no change. Okay, so give me one more. That would cause a shift right.
And
Add oxygen gas. Good. So adding reactant 1 or reactant 2 will cause a shift right. Amy, I think there's one more. Alicia. Gwen? Come on, little table. Let's get it together. You got this. Come on, little table. Gwen's area. Huh? Good. Remove, did you say that?
I said it. I mean, no, Glenn said it.
Okay, thanks, Glenn. Okay, so removing a product will cause more products to be made. All right, so on a scale of 1 to 10, beast mode is 10. Let's shout, what is 1? Let me see where you are.
What?
Beast mode 10. Let's shout, what? Like, you know what it is? 1. I like to vary my ranges here. Okay, good. Hands down.
I think I'm flat.
Go on to my website. Let's practice a little bit more. Pull a piece of paper out. Pull a piece of paper out. Thank you. Yeah, you can do this on your note sheet. That's fine.
Is it related to our notes?
It's all the same concepts. Scroll down to Unit 8. With me? Alright, so scroll down to Unit 8. If you just Google Enloe Cox Mill, it'll come right to my website. It's easier than going through Cox Mills. Okay, so we're under Unit 8. You're going to click on Honors Chemistry Leshat Virtual Lab. Honors Chemistry Leshat Virtual Lab. You have to click more because it's like it's in the farther down the Unit 8 docs. So when you click on Honors Chem Le Chatelier Virtual Lab, this document will pull up for you. Alright, so give me a thumbs up if you've made it here. Thank you. Just trying to make sure we're kind of on the same page. If your partner nearby is not there, just have them look up here for now. So when you click on the link, it does not bring you directly to the simulation. It's going to bring you to like a kind of a home page. So control click, and it'll bring you kind of the home page. Hit Equilibrium and Leshat Principle. So Equilibrium and Leshat Principle, you with me? Clicking this. You control click the link, or if you copy and paste the link, or right click and copy hyperlink, there's a lot of options there. Equilibrium Leshat Principle, and you get this up. You kind of see like 5 or 6 options across the board. So what I'm looking for from you is, and maybe make this one for yourself, you're going to do the background reading, and when you do the background reading, just write down a few details. You can just bullet point out a couple of things. It does not have to be very long. So that's the background. You can look at intro. That's it. Okay. If you want to look at background, there's a little bit more there that you can read. After you look at background, you'll do pre-lab questions. The pre-lab questions are under the hyperlink called pre-lab. There's a little question it asks about like changing color, which you can see the colors are given to you in the written little paragraph right above. After you do the pre-lab questions, you'll hit experiment. And within the experiment, there are 6 options. You see all 6 little pictures here? Yes? Those 6 pictures give you 6 different equilibrium systems. I'm looking for us to get 2 done today. Number 1, which is cobalt, and number 6, which is copper 2 sulfate. So what happens when you click on these little systems is it gives you some stresses. So I click the cobalt one. Here's the reaction. You can see the first guy is blue and the second one is red. So if you're colorblind, have a friend help you, but otherwise you should be able to see some color changes. But if you hit the heat button, it gives you some color changes. If you hit the ice bath, it gives you some color changes. And these others will give you other color changes. The way you're going to document these changes and color changes and shifts are on there's a little table. If you scroll down on the document here, kind of you can write this out, set some up on your paper, and it's giving the system, the stress that you've applied, the color change that occurred, which direction did it shift, and then why. That's what I want you to do for the cobalt one, and then second, the copper one. After you complete those 2 little mini virtual experiments, you'll do the post-lab questions. Any questions right now? Right, thank you. Move on. You can work with the person next to you. If you need the last station you made, I'll give you about 30 minutes right now.
So, is it okay if we do? Yeah, let's go.
Come on. Come on. This order: background, pre-lab, experiment, post-lab.